The hypothesis tests considered so far have been two-sided or two-tailed tests, which means that the p-value is the sum of the probabilities in both tails of the sampling distribution. The two-sided p-value is the probability of the test statistic being as far or further from the null hypothesis in either direction than the test statistic of the sample. For a one-sided test, the p-value is the probability in only one of the tails. The difference between a one-sided test and a two-sided test can also be specified in the alternative hypothesis. In a two-sided test for a population mean, for example, the alternative hypothesis is that the mean is not equal to the hypothesized value without specifying the direction of the difference. In a one-sided test, the alternative hypothesis is that the population mean is either greater than the hypothesized value or less than the hypothesized value. In the t-test function, this choice is controlled by the alternative hypothesis option. For example, starting with a sample and 1000 as the hypothesized population mean, the default result from the t-test function is a two-sided p-value, which is specified by giving unequal as the value of the alternative hypothesis option. A one-sided test is specified by including greater or less as the value of the alternative hypothesis option. Greater, for example, gives a one-sided p-value for the alternative hypothesis that the population mean is greater than the hypothesized value. Since both tails have the same probability, at least in these examples, the one-sided p-value is simply 1/2 of the two-sided p-value. In many applications, the choice between a one-sided test or a two-sided test is arbitrary as long as the results are reported and interpreted accordingly. When the only difference between the tests is that the one-sided p-value is half as big, for example, then using a significance level alpha that is also half as big will lead to the same conclusion about whether or not to reject the null hypothesis. One-sided tests and two-sided tests can, however, lead to different conclusions in the common situation where the test statistic can realistically fall in either tail of the sampling distribution and where both directions are of interest. For example, consider doing a one-sided hypothesis test where the sampling distribution of the test statistic looks like this, with a significance level alpha of 10%, and where the chosen direction of the test is to the right. For this test, the null hypothesis will be rejected only if the test statistic falls in the tail on the right. If the test statistic falls anywhere on the left side of this distribution, however, then the null hypothesis will not be rejected even if the test statistic is well out in the left tail of the distribution. In some applications, this may be acceptable. If a test is done to detect high levels of contamination in food, for example, then there may be very little concern about levels of contamination that are unusually low. Anomalously low levels of a contamination may still be of interest to someone else, however, or at some other time, and so it is appropriate to report such results even if a particular application uses a one-sided hypothesis test. It is generally not appropriate, however, to change the direction of a one-sided test after looking at the data. To understand why, consider a strategy that does include changing the direction of a one-sided hypothesis test depending on whether the test statistic falls near the right tail or near the left tail of the sampling distribution. With this strategy, if the level of significance for rejecting the null hypothesis is 10% and the null hypothesis is true, then there is a 10% chance of the test statistic falling in the tail on the right, and so there's a 10% chance of a false positive in that direction. There is also, however, a 10% chance of the test statistic falling in the tail on the left, and if that causes the one-sided hypothesis test to be done using the tail on the left, then there is similarly a 10% chance of a false positive on the left. The net effect of this strategy is to reject the null hypothesis in either direction with a total probability of 20%, and so this strategy is actually a two-tailed hypothesis test in disguise with a significance level of 20%. To avoid this sort of confusion, it's better to just use a two-tailed hypothesis test. In practice, two-sided hypothesis tests are more common and are generally assumed, except for applications where there is some clear reason to do otherwise. One-sided hypothesis tests will come up, however, in later sections, most notably for hypothesis tests where the sampling distribution of the test statistic is not symmetrical and where there is a clear reason to consider only one tail of that distribution.